机。可以啊，修 NV2 用自己写，相信你写。修 NV2 啊？哦，真的啊？那也很简单啊，那很简单啊，那就然后一个掉了。后来我改掉。对嘛哈？对。对。然后自己写用了。一般做的话，一般都要做对。 go further, I think and almost once you understand the problem, that is how I think it's final. So in that sense, I think I have the tell you to understand what's the signal processing, what's going on there. Okay, so they put one to understand the process. So if you summarize this one, if you remember, first of we try to I use one dimension to do the conclusion from spatial domain, time domain to 3D domain. So the first one is continuous time signal to frequency domain. Okay, so it's time domain to frequency domain. So we use this Fourier transform to represent. So your time domain at the beginning we use some repeat signal. Why repeat is so important? I told you because all the transform from the sinusoid, cosine, sine, and then you know every sinusoid, every single frequency in frequency domain they are only represented by one impulse signal there, right? So you have to understand this one, repeated signal. So it's very important to start with this kind of signal. So it's periodic signal there. So every periodic you can decompose into several different sinusoid, cosine components. So in that sense, after you transform this kind of periodic signal to frequency domain, okay, we use this function, okay, f of omega equal to Fourier transform of f of t. Okay, we use f of t to do that one. So the formula is from minus infinity to positive infinity. So your signal is f of t times e minus j omega t dt. Okay, so it's definition of Fourier transform, right? So what happened of this kind of repeat signal? We call it the Fourier series. So you have to remember this kind of repeat signal. Repeat with a time t second. Okay, so what's the result? As I told you, you have to remember because every repeat signal it becomes a Fourier series. Why? Because the repeat signal can be decomposed to different harmonic waves there. So it's a Fourier transform become like this. Okay, you can see it's become like spike spectrum. So this is we call fundamental frequency omega 0. Okay, minus omega 0, 2 omega 0, 3 omega 0. So you can see your signal, if it is repeat, and in your frequency domain, they will be represented by spike spectrum, right? And every harmonic wave have energy there. So very important. So we start with the Fourier series. Okay, Fourier series represented by Fs. Okay, Fourier series, a series of the spikes, and every spike, the interval is omega 0, 2 omega 0, 3 omega, all harmonic wave. And this one is DC value. Okay, the DC value. How you calculate the DC value? You sum up in the time signal signal and then divided by average as a DC value. So we extended. Remember that one? That's we say if your t increasing, what happened? See, omega 0 is 2 pi divided by capital T. T is your repeat time, repeat periodic time. So when your T increasing, your omega 0 become smaller. So what does that mean? It becomes density, higher density. So if your repeat T become larger, so what's the result? The result tell you the frequency spectrum become higher density. So it become very higher density. So it become like this. Higher density. So if your T increase to infinity, what will happen? What will happen? Your night spectrum will concatenate, connect together, right? So in your frequency domain, you will see a continuous Fourier spectrum. Does that make sense? Okay, so you see, so when your T increase to infinity, so what do you mean? Our periodic signal, this is become non-periodic, a periodic, only one pattern, your signal. So what happened? It become continuous spectrum there. Because very high density, T go to 0, capital T go to infinity, omega 0 go to 0, so they connected together. So you have to understand our Fourier transform come from this fundamental periodic signal. So what's the next step? This is a time domain. You heard, you watch, all the signal is continuous time, continuous space coordinate image. Okay, it's continuous. However, if you want to process it, you have to digitize. You have to digitize your signal into what you have to sample it, right? So how you sample it? So you are going to sample in your signal here. So how do you do that? We taught you a impulse trend, right? Cone function or trans impulse. Okay, it's kind of you are going to sample it. You are going to sample your signal. So if you remember, we taught you the Fourier transform. They have a duality process. So once you see your signal in time domain is like a night spectrum. So what do you see? So it's become like this one. So if you have a signal like this one, and you can expect the result will be what? Right? Continuous spectrum. Okay, and if you can see, it's also become periodic in space in frequency domain. So you can put it in mind. So especially their repeat is a 2 pi there. Okay, so let's see how you do the one. So we call it a discrete time Fourier transform from Fourier series. So always the signal processing you have to understand from Fourier series first, and then extended this periodic signal to single signal, non-periodic signal, a periodic signal, and then we are going to discretize. So let's add one more page here. So we are going to discrete time signal. Become discrete time signal. We call it discrete time Fourier transform. So it's a step by step. Okay, so
you have the discrete time signal. How you do that one? You just times your signal to become discrete. Okay, you sampling. So what you do is sampling. So let's see, discrete time Fourier transform is what I did. I did is try to times my signal become discrete time. So represented like this one. You can write down like this. How do that? Your original f of t times delta series data impulse trend. So see, it's from this one. Every t second you sample 1 point. Every t second you sample 1 point, and it's an impulse trend. So what's the result of this one after transformation, Fourier transformation? So it's based on definition. It's minus infinity to positive infinity, n from minus infinity to positive infinity for the impulse trend. So your signal sampled like this one. Right? It's definition of Fourier transform. But now your signal becomes sample. How you sample? You multiply impulse trend. Every t second you sample 1 point. Every second every sampling time you take one signal there. So it's just like the triangle shape multiply the impulse trend. The result is sample function. So like this one, and from minus infinity to positive infinity. And transform, Fourier transform, into say minus say omega t. So what's the result? Actually, you can see every sample signal become a constant. It's not a time dependent function anymore. So you can take out this one and f of nt here, and then multiply this one that. Right? So what's this integration result? So every function multiply delta function, and then take integration. The integration upper limit, lower limit contain this impulse. There will be a result. What's the result? Your original signal left with the variable replaced by the location of the impulse function. So its a result will become like this. Only this minus EJ omega t, where it happened, where the impulse happened. It happened at nt there. Location of nt. Okay. Delta t minus n capital T, which means the impulse exists in the location of n times capital T second. Okay, so that's the result. So we see your sampled signal, no matter is a one-dimensional or two-dimensional, the result just like this. Okay, so it's a discrete time Fourier transform. It means your signal, your image, your speech is sampled every t capital T second, and the Fourier transform we call it DTFT, discrete time Fourier transform, just like this one. So we write it summarize again. DTFT is Fourier transform of sampled signal. I use bracket instead of the parenthesis. It's sampled signal. Okay. Original is f of t. After sample, we say it's f of n there. Okay. It becomes discrete signal. Okay, so Fourier transform of discrete signal, we say it's equal to what? Equal to summation minus infinity to infinity, f of n to exponential, say omega n. Omega, this one is a new parameter. We say it's equal to omega t, and t is our sampling time every period, and you can say it's equal to sampling frequency inverse. Okay, so omega equal to 2 pi f. So we can get a conclusion. The frequency here can be represented by this. Anyway, if you want to use it, you can see I can use different parameters to describe our frequency domain parameters. So it's a discrete time Fourier transform, right? Just give you a sense. And what's the next? See, our sampled signal transform into Fourier domain, become continuous. This type. And actually, every t second, every 2 pi, if you see this one, if your repeat signal in Fourier domain, omega plus 2 pi, what's the result? Omega plus 2 pi. Okay, so we know we have the f omega here, right? F omega. So how about f omega and 2 pi? What's the relationship between this one? What's the relation between these two? And it's different from here. So omega, if you replace by omega plus 2 pi. Okay, so it's times some integer times exponential j of 2 pi n. And you know exponential j of 2 pi times every integer. If it happens, n is some integer number there, right? What's the result? It's always 1, right? E j theta equal to cosine theta minus j sine theta. Okay, if theta is the integer multiple of 2 pi, what's the result? Cosine 2 pi always E1 equal to 1. Sine 2 pi integer multiple 2 pi, the result will be 0. So it's always become constant 1. So which means in your Fourier domain, the frequency spectrum is a repeated frequency spectrum. That's what we draw here. And every 2 pi, they have a repeat spectrum there. So very, this is kind of duality property of Fourier transform. So in that sense, you see, frequency domain, we have the continuous spectrum. This is complete continuous spectrum, right? Because we do this duality here. It's continuous spectrum and repeated within 2 pi, right? Can you do it your Fourier transform? After you Fourier transform, you do it in your computer? No, it cannot. There are some problems. What's the problem? The first one, you have to face your signal must be what? Minus infinity to positive infinity. So it's an infinite point you have to sample. It's impossible. But it can be overcome. It can be overcome. How you overcome this problem? You just limit your input signal with some specific number, integer number. Okay? Some window. I'm going to process the image like this. It's not the whole big image picture. Only part of image I'm going to process. So what do? You limit your signal within some constraint. Limited. So maybe we say only n points you are going to take a look at. So maybe sorry again. So I should do this one. Add here. So there are two issues we have to overcome. In time domain, I'm going to limit our signal. Big signal maybe in 1 minute, 2 minutes. Image maybe some constraint window, not infinite image. So you can limit it, and you can use it in computer. However, the second problem is they are continuous spectrum in Fourier domain. So how to do it? So the next step is try to discretize your spectrum in frequency domain. So you are going to sample your Fourier spectrum. So the final step is we call discrete Fourier transform. actually all described in your textbook, image processing textbook. So we call it DFT. So how you do it? You have this signal, sample signal, and then Fourier transform become DTFT, become repeated spectrum. There. And 2 pi. And we are going to look at this one and sampleize this in Fourier domain. So the result become discrete Fourier transform. Okay, so discrete Fourier transform actually is not difficult because we know DTFT, discrete Fourier transform, is f omega n from minus infinity to positive infinity. Your sample signal, apply this say omega n there. Okay, so what can we do? We are going to sampleize our spectrum, continuous spectrum, become discrete spectrum. So how to do that one? So we just use this to represent the continuous parameter. I'm going to sampleize, and k is my new parameter in Fourier domain. So from 0 to maybe n point. So it's become like this. So it's become like point only in time domain or spatial domain, limited. And the f of n times e minus j omega k n. What is omega k there? I just told you. I'm going to sampleize the frequent continuous spectrum into discretized spectrum. So we can write where limited signal fn times minus e minus j equal to what? N up. Sorry. Omega k summation and to n minus 1 limited spatial domain signal is n k 2 pi k and what do you mean? One periodic spectrum into n point. N point. The same as your time domain, the same as your spatial domain point. So how many points in spatial domain? How many points in time domain? I'm going to transfer into frequency spectrum domain with the same number point. Sample number, same point. Okay, so it's become like this. And k is from 0. Actually, I use this n. 1 to minus n minus 1. Okay. Right? Because I told you the repeat period is 2 pi. And the 2 pi, you are going to divide it by the distance is n point. So divided by this one. So it's a basic interval in frequency spectrum, right? I'm going to divide it by n point. So the distance between two spectrum spikes is 2 pi divided by n. No, why is 2 pi divided by n? Because I told you it's repeat within 2 pi in frequency domain. And this is parameter k. Yeah, so it's omega k. Every k, the first point, you have the k equal to 1. If you are going to calculate k equal to 0, the frequency DC value, k becomes 0, and you are going to use k equal to 0 here. So depending on which point you are going to calculate in frequency component. So this is the mathematics or the DFT, discrete Fourier transform. The definition is like this one. Okay. So now you know why we can write this directly. It's discrete time Fourier transform, and discrete Fourier transform. 4 different major steps. And we can do it in computer because your signal is temporized. Your spectrum is sampled. You can calculate. You can use a MATLAB to do it. Okay, so we can represent this as a fk omega k as a case point. So we know the final, you can write down like this one. So in your textbook, if we use n replace n, what does that mean? Actually, students just ask me, how you padding 0? Okay, this is also 0 padding issue. Your endpoint, maybe your image is 200 times 200, right? It's not a power of 2. Okay, so how you do it? You can increase padding your image to 256 by 256. All the other location padding by 0 padding. So your M will become power of 2, right? Why do that? Because we are going to use phase Fourier transform. The DFT, the next step is a phase Fourier transform. Your calculation, your algorithm will become faster, much faster than your step-by-step calculation. So how you do that one? You can padding your image to the size of power of 2. It depends on your original image size. I just give you an example. If you have 200 by 200, I'm going to change it to 256 by 256 because 256 is a power of 228, right? So you can use very good high performance calculation for the Fourier transform. Okay, so it's the result is just like this. We use this as a final. Use n is a power of 2, 0 padding, and to represent your image. And E J N 2 pi K N. Okay, so this is the final we're using. We call the endpoint discrete Fourier transform. So in your text example, they use this to calculate, demonstrate for you. Okay, if I am going to text, I'll just give you some simple view, maybe 4 points, and then please tell me what's the Fourier spectrum of this signal. This is 1 dimension. For 2 dimension, it's easy. Okay, for 2 dimension, what's that? Okay, so it's become f of n, n1, n2, f of xy to uv. Okay, so let's use the 1 dimension first. Any question? Oh, let me write down 2D as well. Okay, for the 2D, this is for 1 dimension. For 2D signal, for image 2D signal. So what's the 2D DFT? So you can see we have in class book we use UV as our new spectrum parameter UV, and it's become summation. So it's x from 0 to m minus 1 because we have m by n. Final is m by n image. Okay, without padding yet. Okay, so m minus 1 y from 0 to m minus 1. So it's your image here, m by n. So transform into discrete Fourier transform result. Well, like this one, your f of x, y spatial domain, and then times minus 2 pi n ux plus n vy. That's it. So in your Fourier domain, you have an m by n point as well with the same size as your spatial domain image. And the u from what? U from 0, 1, 2, power to m minus 1. V equal to 0, 1, 2, power to m minus 1. So your m by n image, use DFT to m by n spectrum. F of uv, f of xy. See? So it's just extended from 1 dimension to 2 dimension. And what's the inverse? IDFT. So f of xy can be calculated from your frequency domain discrete Fourier transform result. So it's some coefficient different. Okay, you can normalize. Sometimes we normalize in both space, but here is the traditional way to represent. So it's a uv. Okay, from u to m minus 1, v from 0 to n minus 1. Again, it's fuv from Fourier domain. Switch back to spatial domain. Exactly the same here. And xy equal 1 to n minus 1, y 0, 1 to n minus 1. Okay, exactly the same for the one dimension inverse transform. So we call it the inverse discrete Fourier transform. And after that, you taking your image to the power of some integer, closest integer, and you can use the FFT fixed Fourier transform to speed up your transformation in a low something there. Okay. So we just summarize this for you again, because all your textbook describe this process example. Now later on we are going to look at the image immediately. Please come to think about this relationship of your signal in time domain, spatial domain, and expected spectrum in frequency domain. Okay, so is that okay? Yeah. So this is a whole semester in signal processing from Fourier series. Again, from Fourier series, because your signal assume it's a periodic signal, and you have to know when your signal is periodic-like, your spectrum must be spike-like, nice spectrum. And then you increase your image repeated time to infinity, so it's become a periodic signal. That's the real image, real signal you hear. Okay, except the RE well, otherwise it's all non-periodic signal. So your spectrum become like this. From nice spectrum become continuous spectrum. And then we know the duality of the Fourier transform process. So you are going to sample your signal become like this a sampled signal. And correspondingly, their result will be repetitive, continuous spectrum. Okay, so you sample your signal, you will have this kind of 2-pi repeated spectrum in frequency domain. But we are going to use our computer to do it. Later on, I will teach you how to use it, and the result will become what? You are going to discrete your image, your frequency spectrum become what? Become nice spectrum in your frequency domain, and this is the discrete Fourier transform. So from discrete time become discrete Fourier transform. So either in spatial domain, in Fourier domain, or discretized, or discrete formula. So that's their corresponding formula here. So that's the image processing, and actually you just use FFT2, and you just perform this algorithm. Also, they insert your image to power of 2 to speed up your transformation. Is that okay? Okay, so now you are going to read your textbook, become more easier. Okay, so this is just like we mentioned, your sampled, see your sampled signal, and look at the spectrum. It's a repeat, right? It's repeat, but your signal is only one can represent, and the Umax is your band, your signal band. Your signal frequency, upper highest frequency in your signal content. And how can you do that one? Actually, it's you can design an ideal low-pass filter in frequency domain according to your band limited frequency. You know how to extract your signal in frequency domain. just multiply this one, and you can get this is the result. You can just inverse this signal into your original signal immediately. Okay, so this is the idea. The product of VNA used to extract one period of the infinite period object sequence. Okay, so now the issue happens. So you remember we are only sampling your frequency, your signal in specific sampling frequency. So look at this one. So the signal, one-dimensional signal here, like this one. You know it's we just use a very simple sinusoid, high frequency. Then this sinusoid, right? There are two sinusoid functions. This one frequency is higher than this one. However, if you sample at this blue stuff here, and with this sampling time, please look at this right-hand picture. The result, what? Exactly the same, right? So they must answer no. What's the problem? The problem is your sampling rate is not high enough for this signal. This is just a demonstration, let you know. Your sample result cannot represent your original signal. What's going to happen? Because your sampling rate is too low. So how you do that one? What's the right sampling rate? What's the at least sampling rate for your image, for your speech signal requirement? So go back to look at this one. We just say they are going to repeat. They're going to repeat within 2 pi. Some specific frequency spectrum here. So that's the way you have to think about it. The next is the 1 divided by delta t, right? The omega 0, right? You repeat omega 0 there. And what's the minimal requirement for your sample rate? Which means if this is B, so your frequency band is frequency, right? So your 1 divided by here must be double than this two, double of your bandwidth, your mu maximum, twice, right? This is the B minus B, so the width of your signal is 2B, 2 mu max, or you can use mu max, so 2 mu max, fine. What's your sampling rate there? The sampling rate must be higher than that one. So that's the second requirement. We say your sampling rate must be high enough to maintain your original signal in right result. Okay, so if you didn't do that, see your sampling rate is not high enough, unfortunately. There's some aliens, right? They're going to repeat in your sampling time there, and what happens? The triangle will overlap because aliasing effect. Aliasing is kind of every signal has its identity. However, you didn't separate clearly, so you can see the triangle there, they overlap. So if you use ideal low-pass filter as your signal maximum band B, and then to extract it, unfortunately, this is not the original triangle signal anymore. Because they change. You are going to construct this one inverse. It is not the same as your original signal anymore. Okay, so that's just like you can see, your sampling time is play the key issue, and you have to satisfy this condition. Okay, your sampling must be double of your frequency band, twice of your frequency bandwidth. This is the first requirement. The second is what? Your image must be limited. Okay, so I think we mentioned that one. Your signal is from minus infinity to positive infinity is impossible. So we have to have some limited signal point there. So that's the way we try to describe what's the aliasing effect there? So later on we will see the real example. Okay, and we mentioned this one. 2-unit impulse. We use this one to sample your signal. Yeah, so it's delta. This one, which means you locate as A0, Y0. Okay, from your definition, delta sampling for different time, and this is the 2D function. It's spectrum. Okay, so if you can expect what's the result. Even don't have to use MATLAB to see. You know, it's a profile. It's just a rectangular function, and it's become sync function there. And this is amplitude, so it's become positive or positive or positive. And in two dimension, like a tofu. So what's the result look like? So also in UV, it's also sync function in the other side, and it's become a circle run, so it's look like this one. Okay, so if you look at this one, immediately you say, oh, it's a sync function in 2D, and it's sync of UV. It's become sine U divided by V, sine V divided by V. Okay, so immediately you know the original image should be like this one. So what's the image look like? Which means your image with some white square inside the image, right? If you look at top down, all the background is black is 0, and only center point there's some white tofu, and it's white, and background is black, and the result like this one. Okay, we can see later a lot of examples. Oh yeah, here. See? So this is the image of 20 by 40 white rectangle with a background of 512 by 512, and the size of this one is 20 by 40. Okay, can you expect the result like the right hand side, right? So think about sync function. Now I want to think about it is the width, the height of this rectangular lower than the width of the rectangle. So what's the corresponding in UV domain, vision domain? What the result should be? Because you in spatial domain, time domain, when your tofu is smaller, the width smaller, in width domain become wider, right? Inverse relationship. When your signal, the tofu in your the width of the rectangle in time domain is wider, in spatial domain as frequency domain should be narrower. So if you take the profile and vertical profile, you know the vertical is a small tofu, a small profile rectangle. Okay, and the in x direction is a wider rectangle. So you can expect after your Fourier transform in U corresponding, this is x, this is y, and you can see in horizontal direction become narrower thing. So here take the horizontal line, you see the sync is narrower. Take the vertical profile here, the sync function is become wider. This is smaller, right? In different way. So that's what I told you. I'm not going to calculate the mathematics in class, but for exam, I just give you a lot of different results, different original signal. You have to tell me which one making which one. Okay, the right mention. You don't have to do it, but you have to understand the principle of Fourier transform, and you know what the result should be. So it tell us the center Fourier spectrum show after application and of the log transformation. Actually, it just take a FFT2. We take FFT 2 of this image, input image. Actually, if you look at the magnitude, normalized magnitude, you see nothing because they are very dynamic range, a huge dynamic range. So after normalize, most of them are black. So you have to do some log transformation, make your frequency spectrum in a better presentation. Okay. Yeah. So it's 2D impulse trend. Okay. You know, we take this one to sample your image, right? To sample your image. And what's this result represent for? Okay. This is the example of two-dimensional Fourier transform, oversampled and undersampled blend. This one is oversampled. This one is undersampled. What's an oversample? We mentioned if your bandwidth is a B, so the width will be 2B, 2 times your bandwidth, and your sampling Fs if larger than your 2B, what the result will be? Because oversampling, you waste your sampling power. Because your B is small, maybe 5 megahertz, but you sampling with 100 mega, much. You waste your time because your signal is not so high resolution. You don't need to use very high frequency sampling rate to do it. So it's oversampling. So the bandwidth, the result, they will not concatenate. Okay, if you exactly the same, they will touch. Okay, they will touch together. And if you Fs smaller than 2B, what's the result? Alias will overlap together. Higher frequency part will overlap. Not good as well. You'll lose some your higher frequency information because they overlap, add up together. So no matter what kind of processing after your image filter design, your original image due to your wrong sampling process is already caused aliasing effect. Okay, so let's see this example. The background net is a sampling. Just give you some idea. And there are 3 images. It's thicker and low frequency bar, medium frequency bar, high frequency fixed bar there. Okay, I put that on the sampling net immediately. That image affected by your sampling. Now the graph is look fine. Why? Because it's a low peak frequency for this one, and the sampling net is twice larger oversampling for this one, and this is exactly twice of the sampling rate. So it's fine. You can see your image still clear. Unfortunately, this is a higher frequency, and your sampling rate is more than twice of its frequency. You see the error? Right? Immediately, you can see connect together. Not clearly to see your original. I know. There are some. See? Do you see that there's a line here? I don't know. Maybe it's more clear. Smaller one. You see the line here? Not your original image, but in a curve. It's a curve in your result, image result. There are some wrong image, a curve. After you use the wrong sampling rate, your image immediately has some aliasing effect. So it's just a visualize this one. But later on, we have more examples to show that one. Okay, so let's take 10 minutes rest. We come back to see a lot of examples and how you overcome your aliasing error. Okay, take 10 minutes rest.
现在要换这个。
好，对，等一下换一下。
可以问，这礼拜的考试
到第3章啊。
考到第3章。
对，第3章。有问题吗？第3章 enhancement。
我只是确定一下。
没有，第4章没考，没有，第3章而已。对，好。
我等下那就先播放一下哈，要转的，先不用录，这不用录。它会挡的。我会挡，所以要录就是了。好，那我就录哦。Okay, we talk about aliasing error. Actually, there are two types of aliasing error. Now let's show one example for the temporal aliasing error in the video we'll talk about later. And let me play this one. Just take a look, okay? So, look at this image. Oh, this is just an image. It's different green, and every image graph has a little bit different face. Okay, a little bit shifting, and I'm going to use some spin, and then take a look what the result will be. What can you expect? It's a kind of optical illusion. You see that? And then movement. Clockwise, counterclockwise, counterclockwise, clockwise, counterclockwise. The other image, yeah. Very specific pattern there. Okay, so remember, it's just if you stop. Actually, this is not like this one, and how come they can do that? Show in a different aliasing effect. Okay, so can we go back to our system? So. Okay, so actually see, there's some specific pattern occur. So our aliasing actually there are two different types. Okay, the first type is spatial aliasing. Especially you undersampling. Okay. Undersampling your image. What do you see? You'll see some repeated pattern. Like this one, you see there are some repeated interference pattern occur in your image. Okay, so the second we call it temporal aliasing. It's a time interval. Between image of sequence. Of dynamic range, dynamic image. So actually, from this image is spatial. It's very easy. We will see more examples for aliasing effect. But if your image is sequential image, like a video, and you will see a lot of this kind of pattern. Okay, so it's aliasing time interval between image of sequence of dynamic image. Actually, there's another name called Wagon wheel. Okay, if you want to see the movie, the video, you just type Wagon wheel, and you can see a lot of optical illusion from Google. Okay, a lot of video. They show you what kind of aliasing effect for temporal or spatial aliasing. Okay, so then a lot of interference and some repeated pattern was shown. Let's look at this image. I have to put it larger. So this is the 772 pixel times 548 pixel for this image. I think this is the original image. Try to introduce the aliasing of the resample natural image. A is the digital image of 772 by 548 pixel with negligible aliasing. So mean this image is original one. Okay. The resolution use 700, 500, and this is original image. So how the aliasing happen, especially for this kind of repeat pattern in your image. So let's see this original image. But if we undersample this image again, so the same size, but we use the size of 33%. Only 33% of original one, so it's become 251 and 182. Okay, what does that mean? So the same image, but I sample in different resolution. The lower resolution. You see the aliasing effect. Where? You see the pattern occurred. You see? Actually, here, some pattern. Okay. So it's an aliasing effect. Undersampling your image. How can you do that? How can you solve this problem? How can you solve this problem? Actually, you see some repeat pattern with some higher frequency there. So it's because of your high frequency part, and there are some interference, a little bit difference will be amplified. So how can we do? If we do some low pass filter, smooth filter, first in your image, okay, before we sample it, actually you have to sample first, okay, and then apply some low pass filter on your image and then sample again. So this one is the C image is result of blurring the image in A with an average filter prior to resizing. Okay, the image will be different. So please compare these two images. But you sacrifice some higher frequency components. So you don't like the aliasing. You okay? So how can you do? Try to smooth your image first. So if this example is 5x5 smoothing filter, 1 divided by 25. Now this image more with this smoothing filter, and then font size again. This also small size is a 251 and 128 size, but there's no aliasing effect there. But obviously, this look at the face, it becomes smoother. Okay, blurred for sure, because your low pass filter always has this result. Okay, so here's another example of this pattern. Okay, it's a very famous one. Interference. It's called example of the. Let me change. Example of the Moray pattern. Okay, so they are vector of drawing, not literalized pattern. Superimpose one pattern on the other. Okay, so it's just like a multiply of these two images. So remember, now we are looking at some image, and you take some digital camera to get this picture. What does that happen? Your digital camera, just like this, okay? It's a screen lens, right? This size, depending on your camera's resolution. And you are looking at some repeat frequency pattern. Some repeated frequency pattern, high frequency. Okay, so it's just like your lens modified on this image. It's always happen like this. You will see some spatial pattern occur. Okay, you see that pattern? So real image like this one, but some pattern occur. What's that? Actually, we call it bit frequency. Okay, BAT. If you are interested, look at this one. In Chinese, we call top high. Okay, so it's a little bit different. Okay, so bit frequency, you'll see some interference in your image. Actually, just sample it. If it is from original natural image, unfortunately, there are some unexpected pattern occur. It's called Moray pattern. Okay, it's a Moray pattern here. Moray effect. Moray pattern, and this is another example here. This is also simple, and this is the image there. Some slightly rotated, and then put together, separate, get this result. You see some very regular pattern occur in your image called Moray pattern. Okay, especially when you're sampling resolution a little bit different, they'll magnify this result a lot. Like this. This is the newspaper image. Okay, some magazine image. And for the newspaper, we always use half-tone dot to print out your image. And the newspaper resolution is 75. Half-tone dot per inch for a newspaper. And for a magazine, okay, some magazine, it's 133 dot per inch. So different resolution. But for a higher quality magazine, they use 170, 175, higher quality DPI. So unfortunately, for like this newspaper 75 DPI, as we say, on your image, and you will see some like this pattern. What kind of pattern is it? You take a newspaper, carefully look. You'll see some 45 degree, 135 degree pattern occur in your image, but it shouldn't happen like this one. Original image shouldn't have that one. But unfortunately, it's kind of also the sampling, the halftone. They use printed halftone dot. It's low resolution. So they will create some pattern on your printed image. So how you solve that one? After you learn the image processing in frequency domain, transfer this one to frequency domain. Look at what's the noise, what's the content occurred in this image. What can you expect? We just tell you, this kind of Morley pattern is repeat, right? So as long as it's repeat, what can you see? What can you see? You can see the spike in your frequency domain. As long as you see some frequent pattern, repeat, and you transform into frequency domain, it should be a later chapter. Okay, we have a lot of different theater to design. And you see each one in frequency domain, there's some Fock energy there and some spike, white spot there. What's that? Because of the Morley pattern. Because of your low resolution. That's fine. Immediately you just remove those white spots in your frequency domain. Down. The image becomes very smooth. Okay, in your computer, you can do it immediately. So what kind of filter? We use some notch filter. Remove specific energy in your frequency domain. This image will become very smooth. We will see it later, okay? So no worry, just let you know. During your sampling, during your screening, due to your camera, digital camera, due to your printed machine, because of the low sampling issue, under sampling issue, the Morley pattern will occur, okay? And we can solve it. Okay, so now the homework you are going to have to practice, but I give you some idea to do that. Okay, the first is how you transform your image into frequency domain, and look at it, how you do it. So it's, you can see I have the image there, and I use this FFT2, two-dimensional. If you use speech signal, you use FFT for one-dimensional, and two-dimensional FFT2. I just told you FFT is the same as DFT. The difference is the size will become power of 2. Okay, and it's faster. Okay, there's a FFT shift. I will show that mathematics later. Okay, actually it's try to shift your spectrum. Original, you change to your frequency domain. This is the low frequency part. Okay, and we told you it's a repeat in 2 pi in n point. Okay, it's supposed to be mathematics 2 pi, but depending on how many resolution you did. So it's repeat how many points there. So mn here, right? And this is a low resolution. So the highest one, because it repeats in 2 pi, so the high frequency part should be here. This is symmetric, right? Because we have this repeat signal there. So low is at this corner. But it looks ugly because all your low frequency energy okay at the corner of the n by n size frequency image. So how can we do? How can we do? We know. So you look at this is corner, right? This is a corner. The 0 is down here. So you will see, if you don't do anything, you will see the image like this one and nothing in the between. So how can you do? You are going to shift it into there. So you want to look at this one. So you look at this one. So we are going to shift your result into half of your repeat, your bandwidth. Yeah. So you have to use some FFT shift this program, and then move this one become center, low frequency here, high frequency at the corner. You get it? I'm shifting the triangle. Originally, I look at the half of one and another half, but I'm going to shift one look at the triangle and the triangle located in the center. So the same as this image. So we'll see like this one. This one is not log. I told you because if you didn't do logarithm, you see nothing. Can you see that low frequency here? No. Can you see that? No. So how can we do? We just do some shifting and the logarithm log. Okay. So you take your Fourier transform FFT2, and then we shift it. We shift it because xf. You can shift it x. Okay. So we shift it and we take log. Normalize your frequency coefficient range, and then take a look. So this one is not shifted. This one is shifted. So now can you compare the difference? Can you compare the differences? So it's original. If you get FFT shift, the low frequency here, high frequency here, to another part of low frequency. But if you shift to the center, they'll combine this one here. And high frequency at the corner. Come more clear, okay? About your image. So the linear image after Fourier transform, after shifting to the center, that's a corresponding result. So just follow our suggestion in the MATLAB, and you can look at your image in frequency domain. Okay, so there's more image example. This is the rectangular, right? So rectangular, and this is a square. The square is horizontal, vertical, the same width. So their Fourier transform is either x on u and either v axis. The sinc function should be the same size. Okay, so this is magnitude. So we all take the magnitude. Yeah, take a magnitude, absolute value. It's ABS is the absolute value, right? So the magnitude. We didn't look at the spectrum yet, the phase spectrum yet, only amplitude spectrum. Okay, so it's the amplitude spectrum of the square. So from this one, you know, it's even spectrum. How about this one? This one is rectangular, and vertical length higher than width, horizontal width. So in that sense, in frequency domain, and if you look at it, take an absolute value, So definitely, for the vertical, become the shorter sink. For the horizontal, become the wider sink function. So make sure you understand the relationship between these two. Here's another, we will see another one is some shifting in your spatial domain. Doesn't matter about the amplitude spectrum. We call this amplitude spectrum. You take ABS, okay? Or take ABS, so it's amplitude. The phase spectrum will different in different location, but for amplitude the same. Okay, take amplitude the same. So it's easy. You just design some different and take a look and yeah. So this is you can follow to do that one. So how about this one? It's a rotate, right? Diamond shape image there. So what can you expect? What's the result in your 3D domain? Even you didn't do it, you can expect, right? It's just like a square, so some rotation. So it's dependent on how you did this one. So the corresponding like this. Okay, so it depends on how you design your original image. So how can you do that one? Actually I just calculated this one. Image, I use a mesh grid. So what's a mesh grid? Okay, let me explain the function here. You can play around. So if I use smaller, you can understand what's the mesh grid designed for. 1, 2, 4, 1, 2, 4 in XY direction. So if you use mesh grid function here, actually you can get two matrices. The x equal to in x direction is 1, 2, 3, 4. Give you index, and also this one's in 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So 1 to 4, we have a mesh grid, and we have the corresponding index, and y equal to what? So similarly, it's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So you can easily create the corresponding indices you have to use. Okay. So xy mesh grid 1, 2, 5, 12. So I'm going to create an image with the image size of 512 by 512. And I'm going to create this image here, diamond. How can you do that? How can you design this image? It's just an overlapping. So I have to find, maybe here's a point here. And I look at this summation, the xy location. And if I say it's larger than 364, what does that mean? It's larger than this one. So xy plus together larger than this one. So all this pixel will be turned on as 1. Candidate. Also, x plus y smaller than 568. So I find one point here. You can specify any location you like. Okay, smaller than this one. So should be less than this one. Yeah. So all the pixels here will be turned on as 1, and they are going to use AND operation. So both conditions satisfied, the pixel will be remain. And then find out this one, this point. This one should be, which one is larger? X minus y should be larger than something. And this one will be y minus x should be larger than something, right? So you can take the intersection of these 4 conditions and you get a white box, diamond shape white box. Okay, that's just a trick. How teach you how you create any different shape you like in your image. Okay, is that okay? This one just give you indices, location of your image, like this one. So you can see this one is 1, 1. This is 2, 1. This is 3, 1, 4, 1. X direction, the pixel location, the indices of the pixel location. And I can play around with the coordinate. And then design a new image like this one, diamond shape. Just use some AND operation here. Okay? And I get this diamond shape image there. And look at this Fourier spectrum. As we mentioned, because this is a little bit similar width and diagonal of the diamond, so this one should be look like this. If you have different shape, rectangle rotate in this image, the Fourier spectrum will be different in different angle. Okay, wider become narrower, narrower become wider in spatial domain and frequency domain. Okay. So that's all example for you. So how can I create this one? A circle image, and the Fourier shape spectrum like this. It's circle. Okay. What's a circle? The circle, if you take the profile in different degree, different angle, like in every different degree, actually it's look like a rectangular post, right? Exactly the same rectangular post, just in different degree, circle around. So it's a Fourier transform. We like this one because circle around, every direction have the same function. If you are with the same width, so your same function in different direction, different angle, have the same width. So end up we like this one. If you have an exactly round shape in your Fourier domain, you have a ring effect, a ring-like sinusoid, just like this one. So every profile in every direction, there's a sync function there. Because every profile is a rectangular shape function, right? In every direction. So in this one, rectangular. In the other profile, vertical degree is sync. And they have the same width. So this one looks like a circle ring. How do you do this one? How you create this circle image? Yeah, again, because we want the circle, so our indices can use like minus 256 to positive 255. So it's 512 pixels, including 0 indices. Okay, so it's 512 from minus 1, minus 256 to 255. And we have a new radius parameter. It's use xy square and take dimension of x square, y square, and take a square root. So we have the radius, new parameters. And the new parameter, if it's more than 50, and we are going to do what? To Fourier transform. So this image C is immediately you create a circle image within a 5 tail, and the radius is 50. So depend on your radius. So C is a radius. How you calculate? Because you have all the location. Okay, from minus 256 to positive 256. So the indices. So you try to check smaller than 55 and 15. All these will be turned on as 1. All others will be 0. Okay, so it's very easy to just use a single comment. The radius smaller than 15 is that. Otherwise, it's a 0. So we create this center circle image, and then again take a Fourier transform, take a FFT shift, and you will see the sync all around this image. So That's what I told you. So you have to understand what's the corresponding frequency spectrum of some specific simple image, and you will see the result immediately. Oh yeah, so the final, I think we can think about how to do the shifting, FFT shifting, okay? Yeah, so it's up to here, it's okay? So if I give you image, can you map in the result of the Fourier spectrum? You have to choose, okay? So let's see what's the FFT shift doing. Okay, first of all, you have to know the property, okay? F of x in one dimension, if you times this one, okay. So you can just put it into your Fourier transform definition. You times this one, what's the result? It should be very easy, right? F of x e 2 pi m mu 0 x e summation, sorry, summation. We use summation. Summation n mu x, right? It's discrete Fourier transform, right? Okay, so you can see what's the result. Combine these two. So it's become f of x times minus j 2 pi mu. If you times positive, sorry, positive is one. So minus j 2 pi and the original mu and positive, it becomes minus for there because there's a minus there, sorry. Okay. You just combine these two items with kernel. This item positive with the kernel, and they create a new f mu minus mu 0 there. So if you look at this this formula, it's exactly Fourier transform from x to mu minus mu 0. So the result you can represent is f of u minus mu 0, right? There's a new parameter there. Okay, if you look at the definition, it's a transformation from x to this parameter, from x to this parameter. So if you times this specific component, and the result is just shifting for this position. So if we set the discrete Fourier transform mu 0 equal to 2 divided by n, what does that mean? You have an endpoint in your spatial domain, in your Fourier domain, your image m by n, m by m is fine. If we shift in like this one, so which means you multiply your signal f of x times the exponential, say 2 pi, what's that, m and the Fourier result will be mu minus 2n, right? That's what we're doing, right? We choose your shifting is your half of your image width. Your image width is n point, and I only choose half of it. Shifting half of it, and the result spectrum will be like this one. If the formula is right, and what do you do in your spatial domain, time domain? What does that result? So it's equal to f of x times cancel out j pi x. Right? So what's the j pi x? X is integer. So if x is equal to 1, equal to 2, so it should be right this one times okay, so it's become j pi x. No, I think j pi minus 2 pi 15. It's fine. What's the result of j pi? Sin pi right? J of 180 degree, right? So this one become right. So if you want to shift horizontal location to center of your frequency spectrum, how did you do? In your time domain, spatial domain, you have to multiply this issue. And this issue is exactly the same, -1 x power. What is x? X is your indices in spatial domain. X from 0 to 0, 1, 2 to m minus 1. Okay, we know x is your index in your spatial domain. So if you want to do it, you want to shift your spectrum from original located as a free example like this one. You want to shift to here and -1 to here, okay? Shift to the other position. And what can you do? You just do this one. 1/2 of this one there. You just do this one times every indices power of -1. So what does that mean? The original pixel times -1 to 0 power is 1. The second image pixel will times -1 to 1 is become negative. So if your image is 1, 2, 3, 4. So what's the result? So you become a new image is 1 minus 2, 3, this one. Okay, 2 minus 4, xy. Okay, sorry. But for the horizontal direction, what do? You also have to do this one. So you have to times this one minus times this one. Also in y direction, you also have to do this opposite operation. So it's become -1 s plus y for 2 dimensions. So this become positive, negative. This is a negative 5. As long as the result x indices plus y indices is a odd number, you times -1. If their indices coordinate sum up is even number, you times 1. So it's like this result. -3. Oh, blah, 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 blah. Okay, I'm not going to do this one anymore. So this is FFT shift doing very easy. You can write by yourself easily. Okay, so this I'm telling you this function. FFT shift. What do? Your image pixel value multiply this -1 power of x plus 1. X, Y is your pixel coordinate. So what's the result? The result tells us they will shift to the center of your frequency spectrum. The center is location is n divided by 2, n divided by 2, the location, center of output. Easily. Okay? But mathematically, you have to understand. If you don't do anything, you will get this result. All the low spectrum located at the four corner, high spectrum located at the center part. But if you times FFT shift, will become like this. Shift to the center. How they do it? They just multiply your coordinate summation -1 to the power of this summation. Easily programmed. Okay. So is that okay? So you are doing your homework and design your low pass filter, but you have to do this centralized. Otherwise, the TA will not recognize your result, good or bad. Yeah, you also have to do some log transform. Okay. And you want to look at the frequency spectrum, please take the absolute value before you present your output. Okay, so here's some example again, Fourier transform example, and f of xy, the FUV display as an image. Okay, the MP spectrum. So you see this is a very small rectangle, but in frequency domain become wider. You also can present it in 3D. Okay, if you want a 3D image. Fourier transform example. So maybe I'll give you the first one and the third one and give you the result. You have to make the right selection, mapping, the right mapping. Okay, the small one, the magnitude spectrum become a wider sinusoid, and the median square, the median frequency spectrum, the larger, the denser sync function there. Okay, the size of box increase in spatial domain. Corresponding size in free domain decrease. Okay, I think next we will look at some phase spectrum. Up to here, we only look at the amplitude spectrum. You take the ABS of your Fourier image, Fourier transform output, and you see the amplitude. But also you can see the phase spectrum. Okay, so this is our original image. And we are going to do some Fourier transform. We get a FUV. This is FUV, take a absolute. So what's the result? If you know your Fourier transform, it's become a complex number. So you can separate into image. So we can separate it a real image and imaginary image. Real part and imaginary part. For sure, because your transformation is e to z minus z omega t, right? It's a exponential, it's a complex number there, complex operation there. So it's sometimes you have some complex, some imaginary part data. And those imaginary data give you the angle in the information, the phase spectrum information. So your Fourier transform is complex data layer, real image, imaginary image. So we take the ABS of FUV. What do you do? Actually, we take the absolute value and we take the square of your corresponding pixel square label. Pixel label are the label of your frequency component. Take a square of the real part, imaginary part, and then take the root operation. You get the amplitude spectrum. So how can you see your phase spectrum? So immediately you know it's an arctangent of image UV divided by RUV. Okay, your imaginary part pixel divided by real part pixel. You get the phase spectrum. Also, it's repeat. Okay, within 2 pi m pixel. Okay, so that's a result. You can look at it. So every image Fourier transform, you've got two components. One is the amplitude spectrum. The other is frequency phase spectrum. Okay, in frequency domain. So let's see the real example of the cameraman. So this is the cameraman image amplitude spectrum like this one. Can you tell the difference between this one and the rise? If I give you two images, one is the cameraman, one is the rise, and give you two of this image, amplitude spectrum, can you tell the difference? Can you map it? Result? What's the difference? Do you see that one? A lot of shining. Why? Can you tell me why? Why camera have this energy like the shining? Why? Why? Right? A lot of rod, a lot of stick, a lot of rod. This one will occur in your energy. This one will in this direction. This one will in this direction. The energy stick. A lot of this one. See a lot of vertical rectangle, like rectangle. So compare these two. Definitely, I know this one is belong to cameraman instead of the rise. Okay, so I don't have to do that. But it's a phase spectrum, and you know it's just take attention of imaginary divided by real part. Okay, so we have more. If you measure the wrong phase spectrum, the result will become a disaster. Maybe in the wrong phase spectrum, this is combined with the wrong one, F and G. Rise image with camera phase spectrum, rise amplitude spectrum, and this is a rise phase spectrum with camera amplitude spectrum, and become inverse Fourier transform, IFFT2. So you have a Fourier transform, you can inverse transform it back to your spatial image to look at what's your result. But very important, don't use the wrong phase. Okay, so let's end up here, and we will have a small quiz in Wednesday for 1 hour. Okay. Okay, let's dismiss here. So the quiz will up to chapter 3 only. No frequency component. No worry. Only time domain. Okay.